have something going on. So that's pretty much.
Welcome to the arena for the 1v1 debate.
Excellent.
Well, thank you. Welcome to the arena for 1v1. The principles are Syrus the Great versus Zanick. I am Quantum Eraser. I am the referee. The rules. Real quick. Number one, everyone in the room, please mute yourselves now till the end of the debate. Number two, all direction for control of this debate will come from this chair. When I say stop, I mean both parties shut up. If you don't, I'll mute you. If you continue when unmuted, I'll server deafen and your dumbass will forfeit the debate. Number three, one topic and any related one time. There is no gish galloping, incoherent, bebopping, red herring, incoherent fallacies. I will catch on to that shit quick and stop it in its tracks. Number four, color commentaries about the discussion or your plight will be met with severe contempt and a mute. If there's a second violation, I'll server deafen your dumbass and you'll forfeit the debate. Number five, no interruptions from the audience. They will be not tolerated whatsoever. If I hear a peep from anyone other than the two principals, that's Syrus the Great and Zanick, I'll mute your dumbass immediately. Any questions? From the two principals, topic of the debate.
All right, let's see. I would like gravity, however, with a twist, like the origins of gravity and your universe, your spherical, spinning, heliocentric universe. I want to take it to, where all begins.
Thought you wanted to go Coriolis.
No. I just call you. You're the Coriolis master because you always debate Coriolis. Yeah.
So gravity is the debate?
Yeah, gravity, black holes and gravity. So it's like the origins, in the bigger scheme of things.
Is that agreeable? Zanick, is that agreeable?
Sure.
Yeah.
Who will lead off?
Sure, man. Yeah. All right. Cool.
Who? You?
Yeah.
Syrus the Great.
I think you believe in it. That's what I'm saying. You are right. In the spherical heliocentric model, right? That the universe is a black hole universe, and it all came from like the Big Bang universe theory at the same time. Do you agree to that?
Loosely,
Yeah.
I don't think there's a black hole universe. I think
black holes in the Big Bang universe. Yeah.
Big Bang. Yeah, I think I believe in that theory.
Yeah. Well, we are taught that in like the mainstream. However, they're not. They're mutually exclusive. They're not. You can't add them together because, like, black hole universes are spatially infinite. So it's an infinite universe, and Big Bang universes are spatially finite or spatially infinite. It depends on the K curvature and the energy momentum tensor and Einstein's field equation. So it's determined by the K value, if it's 1 or 0 or -1. Anyways, so they're not. You can't really work them together in the same model, but they do. So how does that? Because gravity kind of starts here, right? Because you can't really formulate these spheres without your gravity, from what I understand.
Right. So mass is boiled down to its bare essence, mass attracting mass. And even at the very small atomic structure levels, things are attracted to one another. They're pulled together. They fill over larger masses. The larger masses have more forces on other objects that are around them, other masses. They pull them together and they clump together, and this clumping forms structures that we call planets and suns and stars and everything else.
Okay. So is everything expanding, or is it stationary, or is it like contracting because of gravitational forces?
It's expanding and it's accelerating.
So all right, in the Big Bang universe, you're right, everything expands. However, in the black hole universe, things don't expand. So which side do you subscribe to, so we can like carry on with that one?
Are you saying that when there was that moment of singularity, the Big Bang, that was a black hole?
No,
Okay.
no, that's not what I'm saying at all. I'm saying that there are two separate models of the universe. However, they lump them together, right? They just add them together. So like universe A plus universe B, right, equals, universe A plus B, whatever that is, And you can't do that because the parameters are different, right? You can't do that. And like, okay, black hole like universes have no age, right? Do you know that? So we're told. According to these, the priests of your like
right.
high science.
Could be a major. It could be a cyclical universe where it expands, it contracts, and indefinitely. You have the cycle of life.
But Big Bang universes don't do that. No, they're finite.
Big Bang. So they
have a finite age. Yeah, according to Hawking. So we can dig this up from like Hawking too.
14.7 billion years ago, we had some reason, some impetus, some spark that started this small, incredibly dense size of an electron.
Okay.
Beyond imagination, and something sparked it to.
Well, we can't do that here.
Wasn't even math.
Okay.
At that point.
Yeah. So
as this expansion occurred,
all right,
everything expanded, and then mass was formed shortly thereafter via this property that we call gravitational attraction.
Cool. So with the something that sparked this electron smaller than the electron. All right. How did this electron thing like? So that it began as this thing, right? So.
Right.
When did you really observe that? It's not, right? It's theorized, correct?
Yeah, they have background radiation, background noise that they can actually attribute to this moments after
the nothingness,
but
with the infinite temperature, because those are the correct parameters. Those are the boundary conditions that we're given about singularity, right?
And then the reason why it continues to accelerate is the $1 million question. So they fill in the gaps. What they observe does not follow the initial theory because they're seeing this.
So all this mass. So was all this mass condensed? Like, was it compressed into this particle?
Compressed.
Or this? It was all compressed. By what exactly caused this compression? Was there a force, external force acting upon it? Because we're so deep in imagination land now, so we really have to dissect, because you are breaking the first law of thermodynamics. We're not second law. We're first law. Like we're breaking the beginning. You know what I mean? Like
no, not really. I mean, if you go with the theory does clearly state that everything in the universe came from this one point called singularity, and nothing was created.
The first law of thermo? No, that's the conservation of what?
Conservation of energy.
Cool. All right. So we're talking about compression, and look, man. Hey, man. If you got a volume of gas and you want me to compress it, I'd be like, okay, sure. I have to spend energy. Period. That's it. So
it's harder to compress gas because gas is a problem.
So solids and liquids are incompressible.
Relatively so. Relatively.
Relatively to I know what you mean, but yes, okay, we both agree the same thing, dude. They're relatively incompressible, okay. However, we have all this solid material, man, like in the so-called universe, just spinning around, and that's incompressible according to the physics we know today. So how was it compressed into that electron? That's one. That's not like the first law violation, right? But okay, there's that too. It's like, okay, dude, like. Double speak, I'm down. Like, just tell me, listen, here you gotta swallow some mathematics, and we're kosher, and I'll tell you, hey, cool, here, swallow
Well,
mathematics.
Okay, no, so I'm not gonna make anything up or have any mathematics other than I do believe a little bit of this is somewhat religious. I mean, imagining the entire universe in something the size of an electron. That's kind of, I wouldn't be betting my life on that theory, right? But that's the theory. So we're talking about the theory. No, it's not mass compressed into this point of singularity. It's not liquids. It's not gases. They're not even atoms. They're plasma. It's things that could be theoretically compressed to this point.
Plasma, according to my knowledge of plasma, I like plasma. I'm no expert, man. I like sputtering and stuff like that, like just kooky stuff.
Too.
So plasma's like, it's super excited gas. So plasma, we're really talking about gas.
Yeah,
okay, you can have a plasma of a metal, copper, sure, man. Okay, but that's still, again, gaseous, super excited gas.
These are still atoms. They're stripped off. Just have an electron missing, or no electrons, right? These are gases. These are still have atomic structure.
Super jittery. Super jitter.
There's no protons. There's no neutrons. There's nothing. This is the substance that they theorize to be compressible, and to use your vernacular, to the point where everything in the universe is in there, and it's not even mass yet. As it expands, whatever sparks it starts expanding. We all agree, or to the theory that this happens. It starts to expand, and all these particles start to coalesce.
Hold on. So it expanded from the initial blast, and then it started contracting. So it started doing work upon itself.
No. There's something that's starting to expand. It's expanding. It's going to continue to accelerate. And while it's expanding, these elements are now attracted to one another, these particles. And of course, mass begets mass, because that's how it works. There's more stages in how these particles become mass. Let's skip over that. Just become particles. They attach to other. They coalesce. There's gas clouds now that are formed. These gas clouds now there's so much mass that they compress and form these. And there was the most simplest element.
I know the hoax books.
Oh, just hydrogen.
But,
hydrogen.
Listen,
and now we have these
basic vectors, man. I know you know some basic stuff. Basic vectors.
So it coalesces, it condenses. We have hydrogen, and we have high temperatures and high pressure that fuses into helium, and that creates a lot of energy, and that creates
beautiful story.
None of these other things.
It's an awesome story.
The reason I'm saying this is because you mentioned earlier about how all the rocks and things. That's way later.
We're getting serious because you have a force going outwards now from this blast that before that it was compressed.
Stop right. Thank you. We're getting off base here. We're going in multiple different directions. I want a claim support. Thank you.
It's your subject, Cyrus. What claim?
Okay. Claimed? Sure, that black hole universes and Big Bang universes are exclusive and they cannot coexist. And your science for gravity takes bits and pieces from whatever you want. That's the claim.
Gravity, the law of gravity being just that object's mass attracts mass. And that is shown by what we can actually experiment scientifically. We can actually take mass, large bodies of mass, and not only witness these attractive characteristics, but we can actually measure it. We can do simple tests, as in dropping something. That's the most simple thing I can think of.
Objection. I'll use it. Objection.
Objection. Stop. Everyone shut up. Objection.
I was talking about the black hole. Yeah. I was saying the claim was black hole universes and Big Bang universes cannot coexist. And like the mathematical part of the space-time continuum stuff, not the Cavendish stuff, which you brought this up. Cavendish does not exist here, right? This is Einstein, Hawking's. So I said you can't lump them together, and you went off like on a tangent to Cavendish. So
yes. Hold on 1 second. His objection is black holes and Big Bang universes are mutually exclusive based on the K value. Is that correct?
The K value would be, for the Big Bang universes, you have to specify which one. Yep. And for the black hole universes, you would also have to specify which one, because there are 4 types, Big Bangs, 3 types, and no one ever specifies.
You bet your sweet ass, and I'm shocked. I am shocked. You know that.
I like my Einstein, man. I like my Einstein, man.
I am here in shock. Zanick, he said that you can either have a black hole universe or a Big Bang. He is absolutely correct. So, do you have a Big Bang universe or a black hole universe right now?
We have a Big Bang universe. That's the theory I subscribe to.
Okay, there's a Big Bang universe.
So, like a white hole, the time reverse version of a black hole.
Yeah, we're not going to no white fucking holes.
All right.
No.
We are going with Syrus the Great.
Yeah.
He is going with a Big Bang universe.
All right. Okay. Finite, infinite, or
Which one?
what? Yeah.
There's 3 of them.
I want to
Okay.
go with
Because
Infinite.
this, okay, so look, I'm not trying to like sound like a dickhead. All right, so in the Einstein field equations, the one on the right with the k value, there's like a minus k something something. Anyways, so that's the energy momentum tensor, and you do have to pick which Big Bang universe you're talking about here. Like you really have to choose to solve, the equations. So you gotta pick your
Okay,
k.
stop. What are you saying, Zanick? There is a K-1, K0, and a K+1 Big Bang universe. Which one are you choosing?
Well, I don't know enough about the choose one that
And-
I think best fits the more likely scenario.
You know
Why don't
what?
you, since we're talking,
Yeah. You know what? I have it in my notes.
show
I've
how
been
that plays a role in each
Shut up.
of those.
I've been searching in my notes for K-1, K0, and K-1 to make sure that you're on board. I cannot find it. Cyrus the Great, can you
Yes.
please explain K-1, K0, and K+1?
Oh yeah, I will have to pull up some notes, but yes.
Please.
I think so. There are 2 cases. I think the finite, I'm not sure which one it is, but so you got 2 infinite cases of that universe and 1 is finite, right? Because when k equals 0, the whole momentum tensor equals 0. Okay, so you're gonna have the 2. Well, I gotta pull up the Einstein field equations. I am rusty on that because it is math. It's been over a year, but that's what I did like a year ago.
You've worked with Einstein's field equations. You've
Yeah, well, look,
reduced them down to, have you been successful in
yeah.
reducing them down to Newton's?
bro. Listen, man. There's a lot of like mathematicians that worked with this. You got De Sitter, De Sitter's empty universe. De Sitter is
Yep.
like a Dutch astronomer,
Yes.
right? Where there's no mass in the universe, mass there's equals 0. It's like what? Okay, so it's insanity. You get like the solutions, like you got different solutions, right, for the Einstein field equation, yeah. So I just go and see what they did. Those guys, the heavy hitters from the ball, and it's just nothing adds up. So what do you mean you got an empty universe? How does that work? But yeah, you can solve it that way. But does the solution make sense? Like, can you have an empty universe? Well, yeah, that's De Sitter's. If you look it up, DI.
He's correct.
Sitter, it's Dutch astronomer, like 1913, something like that, man.
You
But
are
the Big
correct.
Bang, but the Big Bang doesn't really fully explain the origin of the universe, does it? Doesn't
The Big
describe
Bang? No, this is the origins,
It doesn't,
because
it doesn't explain. Does not explain how energy, time, and space were caused. It just describes the emergence of the present universe from this really dense, high-temperature initial state, right?
what got it to this high temperature initial state? Okay, cool, man.
God,
Like we're
maybe God put it there.
okay.
That's
So you want a miracle? I'll give
That's
you a
what I
miracle
do.
here. If all right, then God created the flat Earth. Boom, done. Like if you want to bring in miracles, cool.
We can't-
One
we
for
can't
you,
make-
one for
we
me.
see nothing
What do you
about flat Earth. that you can see, touch, or measure.
Really?
Yeah.
You can't see too far, but that's not the subject.
No, you
Anyways,
can't see too far.
anyway, Bobby, let's reverse. You know, reverse. Yeah. Reverse, bro, reverse. Yep. So, anyways.
Special
Anyways.
relativity doesn't even apply beyond the motion through space, right?
Bro.
Hubbles law. You got to talk about Hubble's law. I mean, there's a lot of Doppler shifts that all lead to this conception.
I'm going to stop.
down.
I'm going to stop it right now. Right now. There's a lot of terms and phrases being thrown around. I have yet to hear claim support. Cyrus the Great, claim support, please.
For what exactly? For the
Bang.
beginning.
Big Bang universe.
Big Bang, Big Crunch. I mean, what's going to happen, right, to us? What's our destiny?
What's our destiny?
The argument?
My prediction.
So it's clear. Hold on. So it's clear to the audience. What is the argument here?
The argument. Hold on, let me pull up my notes.
They call it right now.
It was the origins of the universe, right?
Origins of the universe.
Yeah, origins. Yeah.
Okay.
Origins, like, because the gravitational model like comes like after that, right? It has to, right? You can't precede it. So yeah, we're just talking about the origins and how you can't pick and choose from two different models of the universe, but you guys do. That's it. So
when we talk about the Big Bang, we talk about the observable universe, right? We don't, not the entire universe. We don't know what else is out there. We know things we can see. We know there's things beyond what we can see because things are moving away from us even faster than the speed of light.
But okay, so
but how is that possible?
In the Big Bang, everything is expanding. So you've witnessed the expansion? We've recorded the expansion. Is that correct?
We have measured this expansion.
How did we measure that?
By the redshift and blue shift of objects in the distance.
Ooh, dude, did you study Halton ARP stuff you did on that? I'm really rusty on that, but that's from your ball scientist. That's full of holes. But anyways, yeah.
Well, you don't think redshift is a
no,
thing?
No, I understand it. Yeah. I get it, but no, from what I like, the material I reviewed back then, there were other alternative views on it. You know, and Halton ARP. I remember the guy. Like, the material exists on YouTube, but I would seriously have to go review it. It's a real long time. There's nothing in the head. But okay, so you're saying that. All right, cool. Let's see.
I mean, Hubble's constant and all these other.
What about Hubble's? What's that?
How fast things are. The expansion of the universe based on what they measure. Hubble's law. I mean, I spent a long time for me too. So
okay, all right. So do you have black holes in your? Since you went with the Big Bang, right? Yeah. Okay. Yeah. So my claim is there are no black holes in the Big Bang universe.
There are no black hole. We have a black hole at the center of our galaxy. That doesn't exist.
It can't, according to the math.
Why?
So how does it? Like,
where does the math dictate that cannot occur in the Big Bang universe?
Dude, it truly 100%. You really have to go and study the material. 100%.
Oh, I did a long time ago, but I mean, what I remember is certain conclusions. Like how I derived those or how I arrived at the conclusions. I don't really remember, I'll be honest, but I do remember that.
How many? All right.
Black holes they're all over our galaxy.
Exactly. I was about to ask you that. How many black holes can you have in a black hole universe? How about that? According to like Einstein, dude, like how many? Like, go ahead.
I'm not. I don't know how many. I know there's more than one.
You're supposed to only have one. Yeah. So how come now we got all these?
Wait. Are you conflating the origins of the universe as a
no. No, we're saying black hole universes.
Immortal atom? Are you talking about our black holes we see today in our universe?
They're not. You cannot add them together. These are two different models of the universe. They're not linear. You can't add them together because the parameters, their properties. All right, you can't take a piece from here and piece from there and mix them together. Like a black hole universe, like has a set of conditions, like it has to meet. All right. Big Bang universe has a different set of conditions. You see?
Give me the top three conditions that are different. Give me the top three conditions.
It's not expanding.
Because I have
black hole universes. Black hole universes are not expanding universes. Big Bang universes are expanding universes, okay. And we have recorded. You're saying we recorded the expansion because we live in a Big Bang universe, and we have a black hole in the center of the galaxy that cannot coexist according to the astrophysics that I understood, and that's the mainstream astrophysics.
Nowhere have I ever heard anything or even read anything that talks about any kind of conflict between
Big
Bang and a black hole. No way ever. Never.
I'll lead you to the books.
Stop. You need to stop. Both parties stop right now.
All right.
We have to get some kind of coherent claim, support, appealing to books. Hold on, I said stop. Appealing to, you have to read the books. You have to go research it yourself. No, you have to provide the evidence here in the arena. If this is contention, I understand the argument. I know the argument, but I cannot intervene.
Yeah, I'll have to.
Yeah, go ahead. So either stick to this argument and support it, or change the argument. And Syrus the Great. Hold on.
I know.
Syrus the Great, I am directing this towards you. I'm sorry.
Yep. No, I know. I gotcha. I did not have material prepared, that's for sure.
I know that. You are correct in your claims. I cannot intervene.
I understand.
If you don't have the support at hand, then we have to move on to the next argument.
Yeah, because if you haven't heard of Hubble's law, and I haven't heard of the black hole universe, we're kind of talking past each other.
Yes.
Okay.
Whistling Dixie. So you don't have the your background information on the contrast. You're also disputing my claims that.
Stop. I already said that. Stop.
I know. So let's. Yeah,
Stop.
I agree.
Stop. I already said that. I don't care whether you agree or you don't. Syrus the Great.
Yep. We can move on, man. Yeah, we can move on. That's fine.
That's fine. Go ahead.
I'll have to get material for you, but I can. Sure.
That's fine.
We can move on.
Yes, please.
What would you like to move on to, Zanick? I picked the first one. Go ahead. Coriolis. Reference frames, bro. How many reference frames can you have?
Let's do the Coriolis. Why not? Let's roll down that path.
All right, well, go ahead, man. What's your claim?
Path.
Go ahead.
Let's roll down that apparent path.
Yeah, apparent, exactly. Yeah. I'm down. Go for it. Okay. Cool.
So, but so what's our goal here? I mean, we're just kind of grabbing topics. We have to, they're so wide and so diverse.
We need to fight. Yeah, I know. We're
How
too
does
friendly.
it apply to the overall story we're trying to tell or claim we're trying to make? I mean, if they're related to the Earth, curvature, I mean, what is your God? I mean, what are we really trying to frame this with? How are we framing our discussion for Coriolis so we know which way to go here? That it doesn't have not
in the shape of the Earth, right? Obviously, yeah. Shape of the Earth, yeah.
The shape of the Earth.
Of course, yeah. Of course.
So
right?
We agree Coriolis is an observed effect that is viewed from a rotating non-inertial reference frame.
I disagree.
Oh, okay, good. Then we have something to talk about.
Yes. Observed, yeah. Like, show me. Okay.
Okay, so I can obviously use the most simplest example. You throw a ball on a merry-go-round, and the person that throws it sees the ball. Instead of going to his buddy that's sitting directly across from him, this ball deviates over and curves and flies off the merry-go-round. That's the apparent deflection. That effect is basically called Coriolis.
Okay. On a spinning apparatus, yeah, sure. Centrifuge, yeah, 100%. Let's keep rolling.
Anything rotating. Or
Yeah. Okay, so you were talking about the effect, not like on Earth. I thought you already took it to the ball. No, you were just talking about like that effect itself.
Yeah, so we all agree with that effect, and it has to do with observing an apparent deflection while observing it in a non-inertial, aka spinning, rotating reference frame. Not on, by the way. Not in. In, rather, not on.
In the frame.
In the frame. The frame,
Yes,
the whole
not-
frame,
not on
the
the
whole
frame,
entire
yeah.
point, the whole point coordinate system is rotating.
Yeah,
So
okay.
when we see things, long range artillery, according to the Earth, have these charts developed and distributed to everybody in long range 16-inch gun type of artillery batteries, where they have to take Coriolis into account. That's a huge effect, but it's they could be 70, 80, 90 feet off of their target at 2 miles, but that's enough to where they take it into consideration, just like they would a crosswind. And that is, and the deviations they talk about and are listed in their specifications. When you shoot north, the deviation
south,
is
of
to
course.
the east. When you shoot south in the northern hemisphere, I'll just keep everything in the northern hemisphere to keep things simple and
Yeah.
less pretty. Everything I talk about will be in the northern hemisphere.
Am I allowed to make an objection?
No, you're not.
No.
I'm sorry, man.
No. Who said that?
Cardi.
Cardi, no, you're not allowed to make an objection. Do not interrupt the discussion again.
So these objects will deviate to the east when shooting north. To the south, they'll be deviated to the west. Basically right. They will always be deviating right in the northern hemisphere. And we see examples of
And
that. Artillery was in
The deviation is caused from what exactly?
It's caused by challenging the conservation laws of momentum. So you're leaving from a position of higher tangential velocity when shooting north and
Yeah.
going to an area on the surface of the Earth that actually has a lesser tangential velocity. And
So
that
it's also
difference-
observed in like airplanes, right? If you fly north with like a heli or south, we observe that.
there is something that it's hard to observe it because you're steering the aircraft.
Well, that's how come. Wow. Okay.
It doesn't.
Because that's my method of observation. Like
You
on
need
a
something
shell,
guided.
on a shell, there's too much wind between like point A and point B. Like I know windage will have effect.
Right.
So I can't really take that. Well, sure, yeah, okay, but to
This
verify
amounts
it.
to a crosswind.
So the easiest method of like verification, drones but you still got the wind. So I can't really verify your claim. I understand that it works like on a small scale, but in your like, well, because you already presuppose that the Earth is a ball and spinning. So
No, we're just talking about observations we see. We must assume. Well, it gets better, by the way.
yeah, well, you
Hang on
said
here,
artillery
and I got
shells,
more. I
right?
don't
So
have, this is
yeah,
not-
come
I
on.
haven't become ill prepared here. I have the information that you can observe and or review.
Oh,
here.
I know.
Okay, so we notice these objects consistently deviate to the right when shooting north. In fact, anywhere they're shot, they're deviating to the right. And in east or west, there's an effect called Yeltos, which is also a family of the Coriolis effect, which makes the object basically have less weight. So when it's shot eastward, it has less weight. It goes farther. When it's shot westward, it's
Less weight.
less weight.
Why?
Because it's going along this. It has a centripetal force, which is its weight. Because we all agree objects have weight.
Right, so it's okay. It's got less forces. Is what you're saying? Yeah.
And since it's going on a curved path, since the plumb line of that particular object will always be vector straight down, and that vector is always changing. They're not parallel along its path. It will follow a curved path, so it'll induce a centripetal force. It'll be a centripetal force, and that's
It has been verified. Yes.
Yes, and this is verified. You can weigh things as you travel east and west and see this type of evidence, and that makes things appear 0.3% lighter. Some fraction of a 1% lighter going eastward.
Is it within the margin of error of like or is it?
Device?
Yeah.
No, it's
outside.
It's fairly conclusive that it's
Okay.
it's due to something that's made the object lighter.
I would like to actually look at
these
that.
directions and always in
That would
those
be nice.
directions. I mean, they have a grouping of the bullets for long range snipers that will always appear to be shooting high versus the other direction.
No, I'm not gonna take grouping data as weighing the bullet in mid-flight, like the projectile. No. Okay.
That's the statistics
Yeah. If that's what they used, just scrap that. That just means nothing to me.
All right.
If I thought I actually they had like a sensor because you got to measure the forces, right? Like I thought, like you gotta
Yeah.
right. Yeah.
Yeah, you can measure. So you
That's
can.
how you gotta do it.
Travel in high, it can travel in an airplane. It keeps at a constant altitude. And you can then measure with a very sensitive scale that this object on the scale will be lighter going eastward than it is westward.
Oh, yeah. Well, it wouldn't work on an airplane, but I understand you would have to really fix a device. You gotta calibrate.
No, yeah, it's long enough.
You can't just
Long
airplane.
enough.
Yeah, look at the speedometer. How fast am I going?
Over 4 or 5 hours at a constant, relatively constant velocity. Sure, the velocities will change slightly, and the altitudes.
Yeah, they do. Yeah, they do, man.
That's why the plot is not going to be a straight line. It'll be this jagged line, but it'll be shifted on the lighter side, going east, and shifted on the heavier side.
Well, you assume that the jaggedness of the graph is exactly identical to assume that the shift would be correct that you're implying upon it. You can't do that, man.
No,
Let's see the graphs first. Then okay, if the graphs shift, sure, man.
No,
you gotta match first.
It's statistically significant because all the jaggedness is, the R-square value would actually match the data. I mean, the claim. So it will be significant because all the little jaggeds, which are, like I said, changes in velocity or changes in altitude, any kind of wind you run into, there will be some noise. This noise can be filtered out and get a line that is discernibly below the.
I have not done it myself to verify that this is correct.
I've seen it done, so I'm not going to,
Yeah, sure. We can crunch math all day. I get it. Okay.
And then,
so,
of course.
Yeah, keep going with the Coriolis. Your claim was what?
So because the Earth is rotating, we see these phenomena that can be demonstrated and point to the rotation of the Earth. See, it's like whenever
they all point towards the rotation. Yeah.
The rotation. That we are in a rotating sphere. Yeah. That we are rotating. And rotating specifically because
Okay. Hold on. Okay. Why can't we be a rotating cylinder, and we're just on the surface? I understand that sounds stupid, but if you're going in one direction, it's the same as going around the cylinder. You said a sphere, so.
Sphere, yeah, because we have this Coriolis effect going north and south, and you wouldn't have that.
Yeah, so because you mapped it out. I get it. Yeah, so now you have the shape of the sphere.
It has to be a sphere.
Because we mapped out the sphere based on observing the Coriolis effect.
No, we detect that we were in a rotating reference frame by the apparent deviations we tend to detect.
In projectiles, yes, but not quite.
Projectiles and storm rotations,
not in airplanes because they're under engine power, correct?
Well, they're also being steered, right? And we have the vector of the thrust, which can be changed by a small wingtip dip and a small rudder change. And
same thing on the projectile. It's not in a perfect environment. It's not an isolated.
Well, no, it's not powered or steered.
Oh, well, the wind can actually steer it, yes. And if you have turbulence in the middle.
Well,
okay, if you're measuring wind velocity at point A and point B, but you got turbulence you can't see in the middle. I don't know, man. There's too many variables as a scientist, just basically.
Yeah, no, we can take into account the maximum amount of drag laterally that would happen or be forced on that particular projectile and find out how much it would move it. And we could say worst case scenario, what if we had a 100-mile-an-hour wind along the way? How much would it deviate? Well, we know this profile of the projectile. We know its drag coefficient laterally from the side view, and we can tell how much force would be acting on it in that direction, in either direction, all directions.
Yeah, basic ballistic calculations from the stuff I understand. It does not take account the Coriolis effect at all. It has the ballistic coefficient of the projectile, right? And of course, you got gravity, right?
Well, there's a whole chart.
Projectile mechanics, and you just look it up.
The military not only takes into account the rotation rate, it also takes in the shape, because that's going to change where this thing lands.
The shape of the projectile, of course, yeah.
No, the shape of the surface. It's falling away from you. When you shoot a projectile, you're if you have 8 inches per mile squared over 100 miles, let's say. If you're shooting a long-range ballistic,
you already we don't. You never measured that, but anyways,
that's in the Navy.
You presuppose that you got an 8 inches per mile squared already. But
all right, stop. I'm going to stop the debate right now. There's a lot of opinion, a lot of baseless assertions without any support. This debate is about making a claim and supporting it, whether it be citation or logical consistency, or scientific evidence. Those three. So I like the discussion. It's a great discussion, but that's not what we're here for.
Okay.
So I would say make a claim, support it, shut up, be concise, and let the other have at it. Is that understood?
Yes.
From here on out, for the next 20 minutes or so, I want claim, support.